We are now going to write vectors in terms of I and j. And remember, I and j are the unit vectors. Remember that I and j are the unit vectors 1, 0, and 0, 1. When you have a vector AV, you can rewrite that as AI plus BJ. Because if you took A times 1, 0, that's the scalar A times 1, which is A, and A times 0, which is 0, and B times 0, 1, that's B times 0, or 0, and B times 1, which is B. With the vector 12, negative 1, we have 12i minus 1j, or just minus j. Given vector A equals negative 9.4i plus 7.1j, and B is equal to negative 0.6i plus 3.2j, we want to write negative 2a minus 4b in terms of I and j. Let's go ahead and do the multiplication first. Rewriting A and B with what they are in terms of I and j, I'm going to distribute the negative 2. Negative 2 times negative 9.4 is positive 18.8i. Negative 2 times 7.1 is negative 14.2j. Negative 4 times negative 0.6 is positive 2.4i. Negative 4 times positive 3.2 is negative 12.8j. Negative 18.8i plus 2.4i is 21.2i. Negative 14.2j minus 12.8j is negative 27j. Getting into applications using force vectors, a man exerts a force of 80 pounds on an object by pulling on a rope at an angle of 30 degrees from the horizontal. Write the force vector F in terms of I and j. Remembering our drawing, where you've got some angle measure and some vector, where your vector has a magnitude of v. Let's call this point A, and we'll call this point B. Then the length is the magnitude times the cosine of theta I, because we're in terms of I and j for unit vectors. And the height is the magnitude of vector v times the sine of theta j. So I can write vector v as the magnitude of vector v times the cosine of theta I plus the magnitude of vector v times the sine of theta j. So we're going to write our force vector like that. So force vector instead of vector v is going to be equal to the magnitude of F times the cosine of theta I plus the magnitude of F times the sine of theta j. And I is left and right, and j is up and down. So we've got this theta angle of 30 degrees. And we know that the force on the object is 80 pounds. Then the vector, the force vector, is given by 80 times the cosine of 30 degrees I plus 80 times the sine of 30 degrees j. The cosine of 30 degrees is root 3 over 2. The sine of 30 degrees is 1/2. I grab those values from the unit circle. The force vector is then equal to 80 divided by 2 is 40, so I have 40 root 3I plus 80 divided by 2 is 40J. A ball is thrown from a height of 1 meter. At a time of release, the velocity of the ball is given by the vector 27.2I plus 12.7J, where each component is given in meters per second. Find the initial velocity and the angle above the horizontal at which the ball is thrown, round to 1 decimal place. Let's draw a picture of this. We have our angle theta. We have our 1 meter height that we're throwing the ball from. We know that the horizontal component is 27.2I and the vertical component is 12.7J. The magnitude is the initial velocity of this ball being thrown. We find the magnitude by taking the square root of the A value squared plus the V value squared. We want to find the angle as well, and remember that the tangent of that angle is equal to the B value over the A value when A isn't 0. So we can say that the inverse tangent of B over A equals the theta we're trying to find. The initial velocity is equal to the magnitude, and the angle is found by taking the inverse tangent of B over A. The initial velocity is then equal to the magnitude of the vector, which is the square root of the A term squared plus the B term squared. That's the square root of 27.2 squared is 739.84. 12.7 squared is 161.29. That is the square root of 901.13. We then have an initial velocity or magnitude of the square root of 901.13, which is 30.02, which is 30.0 rounded to 1 decimal place. And our velocity is measured in meters per second. Theta is equal to the inverse tangent of our B term of 12.7 over our A term of 27.2. You need to make sure your calculator is in degrees. Evaluating the inverse tangent on calculator, we get that theta to 1 decimal place is 25 degrees.